Okay, in this section, section 3.4, we're going to talk about inequality functions and how to solve them both graphically and algebraically. The first part we're going to talk about are polynomial inequalities. And we're going to tackle this first part right here with solving a polynomial by using its graph. So I have an example here. The first example says I want to solve x plus 3 times x minus 1 squared, and I want to know where is that greater than 0. So here is a picture of that polynomial, and basically what it means when you solve it is you're going to find the interval of x where the graph is above the x-axis. Now why am I saying above? The reason I'm saying above is because this part of the polynomial has to be above 0. Okay, so if my polynomial is greater than, then I'm looking for it above. If it's less than, I would be looking for below. Now something else I want to point out, just because you'll be asked for it at some point, when you have a greater than or a less than symbol like we do here, then we call this strict. So we have a strict symbol here, okay? And you just need to know what that word is. Okay, so I'm looking for the interval of x where the graph is above the x-axis. So if I were looking at this, I could say, well, between -3 all the way over to 1, the graph is above the x-axis. And then right after the number 1 and on to infinity, it is above the x-axis. So if I were going to put parentheses here, I could put parentheses around this first group, and then I could put another set of parentheses around the second group. Okay, now why do you think I cannot include these two intersections, these 2 points right here, the -3 and the +1? They're not included in my solution because I cannot include the actual intersection points. I can go right up to the intersection point, but I can't include the intersection point, okay? Which is why I used an open bracket right there. So the solution to this would be from -3 to 1, union 1 to infinity. And that's the way that we would write this, even though this is repeating that number. By including the brackets and the parentheses in the union symbol, we skirt around, we basically include that hole right there, okay? So this is the solution graphically. You're just basically looking at the picture and either figuring out where the graph is above or below the x-axis. And that's pretty straightforward. Okay, so now we want to talk about how to solve a polynomial inequality algebraically. And before I begin, I want to point out this formula here for factoring the difference, and it could be either the sum or the difference of two perfect cubes. Now, I never can remember this formula, so I'm going to write it down right here for you. I don't expect you to have it memorized either, but I do expect that you can use this formula. So before we go any further, let's see how you would break this down. If I had a perfect cube minus another perfect cube, only two terms, I would take this, and we take the cubed root of the first term minus the cubed root of the second term, and it breaks up into a product of a binomial times a trinomial. And it'll be easier when we have some actual numbers instead of letters in a second. Okay, so we want to solve the inequality x to the fourth greater than x. And if we'll just follow the steps that we have listed here, then this won't be as bad as it seems. The first step tells me to write the inequality so that all my variables are on the left and there's only a 0 on the right. So we are going to subtract x from both sides, and we end up with x to the fourth minus x greater than 0. I just moved everything over here to the left and zeros on the right. Now the second step tells me that I need to determine the real zeros, or the x-intercepts, of the graph. Traditionally, when we've been told that, we set our function equal to 0 and solve for x. And now that I'm doing this, I can see that I can factor an x out of both of those terms, it leaves me with an x on the outside, x cubed minus 1 on the inside. And I hope that you recognize that this first x cubed is perfect and the 1 is a perfect cube. Okay, so I have two perfect cubes and the difference of my two perfect cubes. And I'm going to use this formula up here to be able to factor this binomial. So this x just comes straight down. And in the first set of parentheses, I'm going to take the cubed root of the first term, which is x, minus the cubed root of the second term, which is 1. And I'm going to use these two values right here to come up with the trinomial portion over here. So I'm going to take that first term, which was an x, and I'm going to square it, and I get x squared plus, because that's what the sign is. Now I'm going to multiply these two numbers, just the 1 and the x, so I get x. And then I'm going to square the last term, which is just a 1, plus 1. Okay? So this binomial, this the difference of these cubes, factored into this term times this trinomial right here, all equal to 0. Okay? Still continuing, trying to figure out what this is going to solve like. I know that I have x is equal to 0. I have x is equal to 1. And over here, I have x squared plus x plus 1 equal to 0. Well, I can do the discriminant here really quick to see if we're going to get any type of real answer. And when I do that, remember the discriminant was b squared minus 4ac. b squared is a 1 minus 4 times 1 times 1, and I can see that I'm going to end up with a negative 3. In other words, this trinomial is not going to factor on the real number line, so we can just throw it out. So, step number 2 completed. We determined the real zeros of the function. Now we're going to take those real zeros and we're going to divide up a number line based on these values right here. Okay? So, let's draw us a number line. I'm only interested in having a 0 and a 1 on here. Okay? So I know that anything less than 0 is going to have some sort of interval that looks like negative infinity to 0. In between 0 and 1, I have the interval 0, 1. And to the right of 1, I have the interval 1 to positive infinity. Okay? Now, these are breaking up a number line into possible solution tests. Okay? Into intervals that we have. Now, after I've broken this up in intervals, we're going to pick test points. Okay, so over here, I'm going to pick test points in each one of these intervals, and I'm going to plug it into the original function to find out whether or not I have positive or negative values. And that'll be just a little bit clearer in just a second. So I'm going to rewrite my original function. The original function is x to the 4th minus x. And that's what I'm going to plug my test values in. But here in this far left-hand interval, I'm going to pick, and this is totally at random, I'm going to pick a number less than 0, so I'm going to pick negative 1. Then I'm going to pick a number in between 0 and 1, and I'm going to pick 1/2. And on the right of 1, I'm going to pick 2. Okay, so it doesn't matter which numbers you pick as long as they fall within these intervals. Then I'm going to take each one of these test points, and I'm going to evaluate my function at that test point. So I'm going to evaluate the function at negative 1. If I plug in negative 1 to the 4th minus negative 1, I end up with, this would be positive 1 minus minus, so I would still have a positive 1. I would end up with, so I'd have 1 minus a negative 1, change, and I get 2. So in other words, in this first interval, if I were to plug in a negative 1, or if I plug in anything, basically, to the left of 0, I come back with a positive value. And that's all I'm looking for. Let's try that again over here. I'm going to evaluate the function at 1/2. Okay? So I get 1/2 raised to the 4th minus 1/2. Okay? 1/2 raised to the 4th would be 1 over 2 times 2 is 4 times 2 is 8 times 2 is 16. So 1/16 minus 1/2. I don't even have to do this on my calculator to know I'm going to come up with a negative value right there. So I know that in this middle section, I have a negative value. And then to the right of 1, we're going to evaluate the function at 2. So I get 2 to the 4th minus 2. Well, that's going to be really big minus not a lot. So I get a positive value to the right of 0. And what that has told me is it's telling me how I'm supposed to write my solution. The question said, I want to know where the function x to the 4th minus x is greater than 0. So if I'm looking for where the function is greater than 0, then I'm looking for where the function is positive. And up here in our test points, let me go up a little further. Up here in our test points, we can see that on the interval from negative infinity to 0 and on the interval from 1 to infinity, I have positive values, and that right there is the solution. Okay, so I would have negative infinity to 0, union 1 to infinity, and this came from breaking down my my number line. And we would graph this so that it looked like 0 and 1 and draw my shading in the appropriate directions with the parentheses like that. Okay? So for a polynomial inequality, I was only interested in the solutions that were greater than 0, and they happen to fall to the left of 0 and to the right of 1. Okay? All right, let's try that again. So basically this was my answer. Okay, the next example I have says x cubed minus 6x squared is less than 0. So I can skip down to step number 2 because I already have my variables collected on the right-hand side, on the left-hand side. So step number 2 tells me to find the variables, to find the zeros, which means I'm going to set my function equal to 0 and solve for x. Okay, so I can factor an x squared out of each of those terms, and it leaves me with x minus 6. So I know that x is equal to 0 and x is equal to positive 6. Okay, so that's just factoring and solving. Now let's take those values for my zeros and let's divide up my number line according to my x values. So I only have to put on here a 0 and a 6. I'm looking at, if I was looking to the left of 0, my interval would look like negative infinity to 0, 0 to 6, 6 to infinity. Now, I'm using parentheses in all of these because I'm looking for either less than or greater than, not less than or equal to. Okay, so now that we divided up my number line, I'm going to have to pick some test points. So over here, again, it doesn't matter which test points you pick. I'm going to pick negative 1, 1, and 7. The smallest numbers I can think of. Okay, and my function that I'm supposed to be looking at, again, is x cubed minus 6x squared. So I'm going to evaluate each of these points in my function. And I'm only interested, again, in whether or not my function ends up being positive or negative. So f of negative 1 gives me negative 1 cubed minus 6 times negative 1 squared. So this would be negative 1 minus 6, giving me negative 7. So in this first division, I have a negative value. Now what happens if I evaluate the function at just 1? I get 1 cubed minus 6 times 1 squared. which would be 1 minus 6, which would be negative 5. Again, I have a negative value in the middle portion. And then when I evaluate it to the right of 6, for f of 7, I end up with 7 squared minus 6 times 7 squared. No, this is a cube, I'm sorry. 7 cubed minus 6 times 7 squared. Okay, and I have a really big number minus not as big of a number, so I'm going to end up with a positive value for the last section. So my solution then, it helps me to rewrite my original inequality statement. X cubed minus 6x squared. I'm looking for solutions that are less than 0. So in other words, I'm looking for answers that are going to be negative. So here I have the interval. This first section right here was from negative infinity to 0. And this was from 0 to 6. So I'm actually looking for the interval from negative infinity to 0, union 0, 6. Because both of these intervals give me that negative value. And then if I wanted to graph it, I could using the rules that we had above. Okay? So that's how you're going to graph and solve algebraically a polynomial inequality.